I first met Casey at the VelocityConf in California a few years ago, and I think the topic of conversation was this idea he had for the Chaos Manifesto, and it was just an idea. And now, today, he's the author of the Chaos Manifesto, nothing to do with me, really, and also the author of the Chaos Engineering book from O'Reilly. So please welcome Casey Rosenthal.
You heard it here first. Archie was the inspiration for chaos engineering. So DevOps is about surprises in production and improvisation and adapting to that. So I'm going to improvise a little bit, and I'll have you improvise a little bit too. I was going to give a talk on faultless systems. Now that I understand the format to DevOpsDays a little bit better, I think that's probably a better conversation for one of the open spaces or lunch conversations. So instead, I'm going to focus a little bit more, something very much related but slightly tangential, which is complex systems. And hopefully, I'll posit some things that you disagree with, because that makes for more interesting conversation. So not really, but my talk is called Faultless Systems. What do I mean by a complex system? I'm going to describe a microservice architecture, not because I don't think you don't know what a microservice architecture is, but just to highlight a couple features of it, and so that we have a common understanding to talk about complex systems. So I used to work at a small video streaming company called Netflix. They have a microservice architecture. Here's a picture of it. They have 7 microservices. If you have a device like a smartphone or television or a laptop, that might submit a request to the control plane at Netflix, which comes into, let's say, a proxy. And we'll call that microservice C. Now, of course, it's a proxy, so it doesn't have all the information it needs to respond to that request. So C reaches out to A and F. And A might be a microservice about like customer data, and F might be data about like movies or something. And of course, they don't have all of the context that they need to respond to that request either. So A reaches out to B and D. F also reaches out to D, but it also reaches out to G. And then G reaches out to E, and D does as well. And then E reaches back out to A. And so these microservices talk to each other. And once they get their responses back, they collate that, and a response is emitted back to the device that initially made the request. Cool, everybody understand that? So that's a microservice architecture. That's how Netflix works. The interesting part from a complex system perspective is the spaghetti of communication between the different actors, the different microservices. Except I fibbed, Netflix doesn't have 7 microservices, it has over 100 in the critical path just to stream a movie. Here's a picture, a screen grab taken from an internal tool called Visceral that shows internet traffic coming in from the left and fanning out among the microservice dependencies just to serve video. Needless to say, this gets kind of confusing. In fact, I will just take it for let's say the rest of the day, that a good definition of a complex system is one in which you can't fit all of the moving parts in your head. Okay? So you can't mentally model how this system works, at least not with any high degree of accuracy, because there's too many moving parts. Okay? Why would you do that? Why would you build a complex system? Most engineers can explicitly optimize for one of these 3 things, particularly in a stateful system: performance, availability, or fault tolerance. Just to differentiate between availability and fault tolerance, like a bank, but some bank websites still go down on Sunday. Banks don't really optimize for availability, but they optimize for fault tolerance. They never ever want to get a bank account, a balance wrong. Whereas a massive online video game will optimize for availability. They never want to go down. They care less about whether or not something is wrong or incorrect. So they will optimize for availability over fault tolerance. Really good teams can optimize for these 3 things consciously, simultaneously, and figure out how to make trade-offs, right? So Netflix added a fourth one, which is feature velocity. Not just process-wise, not like, oh, well, let's be agile or do something else, but how can we construct our architecture to enable us to deliver features faster? And so that's why they chose a microservice architecture, because the decoupling of the deployment process among the different teams allow them to deliver features faster. So like when you look at the engineering structure of Netflix, it's more akin to 100 small teams of about 5 to 7 engineers each than it is to like one big organization. Why is that a problem? Let me illustrate really quickly just one way that this could be a problem. Complexity really can be a problem. Here's a close-up of a microservice setup. We'll say that P is a microservice for, I don't know, people. And so data from people comes in, and it gets saved, and you never have to delete people because, like, you know, we can just let that data monotonically increase. So it's really easy. It just saves data about people and then serves that data back out. And it passes the request along to Q, which just handles the stateful transactions. Okay? And so Q says, all right, well, I'll save this on write. I'll save it both in a column data store, maybe that's Cassandra or DynamoDB or something, and I'll also save it to cache in Redis. Very typical setup, nothing interesting there. We can go a step further, right? Maybe we'll call this best practices, and we'll say, okay, we can wrap these requests so that if on the read path, say the cache fails, we'll pull from the database. And if they both fail, then Q has some default response that it'll emit. Same for P. It can catch errors, or if Q just doesn't respond, it'll have some default response. So this is taken from a real example. So one day, Redis goes down. Happens, but no big deal, because we've got redundancy in place with the column store, and we're catching the responses. So Q goes, okay, so I'll pull this data from the database instead, which works up to a point, but then it starts to slow down, because this has been in production for a while, and what went unnoticed was that the workload was actually very read heavy. So it's reading from cache, which is very fast, and so then you miss out on the fact that when you don't have the cache and you've got all these reads, the database, the stateful database, can't handle that read throughput. So that starts to slow down, and eventually it stops responding. The latency gets too high, and it misses things. So Q reports, says, oh, well, you know, I can catch that, and I'll handle, I'll just pass along a default response of a 404. Which is what databases usually do when they can't find the data, or when one of their internal nodes stops reporting. So Q passes a 404 onto P. But we don't delete people. And so P has an ID for a person, and now it's looking that person up. And while P had a wrapper to handle an error or no response, it has nothing to handle a 404, because that just doesn't make sense. So P goes down and takes the whole system down. Whose fault is that? Oh, really? Does anybody want to like? No. So that's nobody's fault. Nobody did anything wrong here. All of the components in your system could be 100% provably correct, and yet the system could exhibit undesirable behavior. That's one of the interesting things about complex systems. So, like, again, you could have 100% test coverage on something, and stuff could still not work out. So, how do we handle that? How do you handle that in or outside of DevOps? How do we survive the undesirable effects of complex systems? The go-to answer that I hear the most often is simplicity. Simplicity is the opposite of complexity. So let's just take the complexity out of our complex system. How does this work? Well, first, let's understand complexity a little bit deeper. We can classify two different kinds of complexity. One is accidental. And if you write code, you are creating accidental complexity. It's like dirt that comes into your house. Nobody brings it in on purpose, but it just eventually you have to clean stuff up. Well, I have 2 little boys, so they actually do bring dirt in on purpose. But accidental complexity, if you're writing code, you're adding this because anything you add is going to add some degree of complexity. So it turns out that there aren't any practices or methodologies that can sustainably reduce the complexity of a system. So in theory, something like TDD can maintain a level of complexity, but not reduce it. You can have spikes where you go, okay, I've got a very complex thing here, and so I'm going to focus on rebuilding it or regutting it. And aside from second systems effect, which says that probably won't work, maybe you can pull it off and you can have a temporary reduction in complexity. But as far as we know, there's no system that can do this sustainably. So accidental complexity is just going to kind of happen. And then you've got another kind of complexity, which is essential complexity. This is the stuff that you add on purpose because there's a business reason to do it. It's probably why you were hired. Let me give you an example. Imagine you've got the simplest database you could imagine running on this very high-tech looking laptop. It runs in memory, it's key value. You give it a key and a value, it saves it. You give it just the key and it returns the value. Can't get much simpler than this. And then there's a business imperative. Okay, I want this to be more available. All right, first thing we can do, we can put it on the cloud, right? That way when I close the lid to my laptop, the database doesn't disappear. So now it's more available. What else can we do to make it more available? Well, we can put it behind a consistent hash and have different nodes with different partition mechanisms so that multiple nodes have the same data. That's a pretty available database. What else can we do? We can make it master-master, have those clusters talk to each other and sync up in different regions of the world. Okay, in less than a minute, I've described some best practices that are fundamentally very well understood for how to make this database super available. Let's go back to the simple one. Now tell me how you would make this more available and simpler. You can't. So, to get work done, you're going to have to add complexity. So making something simpler is just going to give you gray hair. It's just going to cause friction. It's not a solution for handling complex systems. So back to the question, what can we do then? Redundancy. Well, that's how we solved the database problem, right? We added a bunch of redundancy with nodes. Quick tangent into engineering, because all engineering is the same. Rocket engineering and software engineering. It's totally the same. So I won't date the audience by asking if you remember the Challenger explosion, but some of you probably don't remember it. So in 1986, in the middle of the height of the Cold War, the US had a shuttle program that was about 5 years old. And the Challenger shuttle exploded shortly after taking off. Now, in addition to the loss of life, what made this particularly poignant was in the year prior, NASA ran a competition to find America's teacher. And the winner of the competition was on the shuttle. She was the first civilian to fly on a space mission. Well, she was the second. The first was a congressperson, though, so nobody cared. So she was the second civilian to fly on a shuttle. And because she was a teacher, a lot of us in school at the time had the feed from NASA, from the launch pad, playing live. So a lot of us remember where we were when this happened because teachers ran in front of the TV screen horrified and tried to turn it off very quickly because We never seen something like this on live television before. And the great thing about studying this is that there's so much data. They had like a year-long presidential commission where they interviewed everybody involved. How could NASA fail? They had the best and the brightest. They had redundant systems. They had so much money and time. And at this point, experience about 55 shuttle missions prior to this one exploding. How could they fail so monumentally when the cameras were rolling? And the Presidential Commission basically concluded that management was inept and had covered up known risks to the flight, and that there was an engineering problem, particularly with O-rings. So what exploded was the white rocket attached to the red rocket. And I'll talk a little bit about how that's constructed. Here's a live picture of an O-ring. Ta-da! The way that the rocket is constructed, it's not built in one long piece. It's built in sections, and those pieces of tubing basically fit into each other. So you can see in the inset here that it inserts into a lip there, and at that seam they have 2 O-rings to make sure that no heat from the rocket burning escapes. The heat that escaped that caused the explosion was about 0.04 inches of space for a few milliseconds. So it doesn't take a lot to set this thing a kilter. And here's another picture of an engineer holding a cross-section so you can get an idea of the size of the O-rings there. And here's a bigger inset. So there's 2 O-rings. There's the one at the top is the primary and then the secondary. And they would cover this on the inside with putty so that heat couldn't get through. So what happened? Well, by about the 5th mission, the 5th shuttle mission, the white rockets would fall off after they were spent and fall in the ocean. So they could collect them and analyze them and see how it did. And by about the 5th one, and I'm way overgeneralizing the storyline here, but by about the 5th one, they noticed that there was some heat damage to the primary O-ring. Okay, so why didn't they stop the shuttles there? Well, for one thing, they had hundreds of things that didn't go quite as planned, but this was within the error margin. They had the redundant O-ring, and obviously the shuttle was safe because it came back. So it was within their experience margin. So over the next few years, they flew more missions. Sometimes there was no damage. Sometimes there was some damage to the primary O-ring, but it was always within the error margin, and it was always confirmed by their experience with the shuttle coming back. And so they did things like they changed the way that the putty was applied, and that would reduce the amount of damage sometimes. And then over the years, they would do other things, like they had one mission where there was a lot of damage to the primary O-ring. So after that, they put an air pressure nozzle between the 2 O-rings and put a lot of air pressure in there to make sure that those were sealed really well. Well, it turns out that created some air bubbles in the putty, which created a venue for more heat. And so that primary O-ring on that mission was damaged even more. And so they dialed down the pressure that they used and had less air bubbles in the putty, and so that worked better. And then in the year before the explosion, in early '85, heat actually made it all the way through the primary O-ring, and there was some damage to the secondary O-ring. But again, thank goodness they had that redundancy, and that was still within their error margin, and that shuttle came back, so it was within their experience base. Up until it wasn't. So why did they continue to fly these missions? 1, the functionality had redundancy. 2, the deviation was within their experience base. The shuttles kept coming back. And the issue was self-limiting. They thought the increased pressure on the O-ring would make the seal even tighter. This mirrors how a lot of us think about our running systems. If they didn't have that redundancy, they never would have done the 6th launch, let alone the 55th, because they would have stopped the launches and they would have fixed the primary O-ring properly so that it never had damage. So in this case, while there's no root cause, having the redundancy of that secondary O-ring was an enabler for the accident. Despite designers' best intentions, redundancy can unwittingly increase the chances of an accident by encouraging operators to push safety limits well beyond where they would have had such redundancies not been installed. So Snook was talking about Black Hawk helicopters, where they've got two motors, a primary and a backup, right? Which is really good. If you're out in a war zone and your motor dies, you want to back up so that your helicopter can keep flying. Except that the pilots knew this. So they would run the helicopters faster and further than spec, burning out both motors, making the helicopter less safe than if it just had the one primary motor. This happens. Okay, so redundancy isn't going to solve this for us. Safety. I like to pull from this study in Squirrel Academia. It's a little bit more interesting than some of the human studies. So there was a study on squirrel car safety, right? So squirrels run around collecting acorns and chestnuts. They have a lot of car accidents. So the squirrel academic community, ran this study on how to be more safe about gathering acorns and chestnuts. And their first conclusion was, oh, well, the safest thing you can do is to just not chase for chestnuts and acorns. Just stay home, don't move, and you're really unlikely to get in any car accidents. Just relax on a hammock. This is true for software. If you don't change your system, turns out that's a lot safer than making changes. But they have other imperatives that drive them to actually seek food. So through their analysis and research, they found that some squirrels are so risky that they die. That's pretty obvious. That's the downside of risk. But the safest squirrels are the ones who are very risky and don't die. Not the squirrels who are the most resilient squirrels are the ones who take a lot of risk and don't die. Not the super safe squirrels who are rarely exposed to car accidents. Turns out they're not very resilient, and they have higher error rates. And they communicated this through the animal chain. It turns out that humans replicated this study with deep sea fishermen and captains. And so the same applies to people. So if you're looking to be safe, you're actually damaging the resiliency of your system. It's only through exposure to risk that you can be resilient in a system, which is a little bit controversial, but the empirical data shows that it's true. What else can you do? You can have insight into how to navigate complexity. So there's this theory called the economic pillars of complexity. 4 things that they consider in this economic model: states, relationships, the environment, and reversibility. And the quintessential example of this model is Ford in the 1920s. You can have whatever car you want as long as it's a black Model T. Right? So the states for the product are limited. And the relationships were limited too. In the assembly line, like, you can talk to the person to your left and maybe to the person to your right, but it's not a team that builds a car and that's very interdependent, and then they build another car and it's very interdependent. The relationships between the moving parts has been reduced. Nobody can really do too much to control their environment, and reversibility is a very hard problem in auto manufacturing, unless you just put your car in reverse. So they couldn't do much there. Software, unfortunately, can't control these things in the same way. The number of states in your software, generally you have a business imperative to increase those because you're going to want to increase the functionality. The relationships, the things that we are building and using to build our software, increase the number of relationships. Distributed systems have more relationships. Microservices, container platforms have more relationships. So those things are increasing. That doesn't help us navigate this complexity. We can't do much about the environment, but reversibility, that's someplace that software excels at. So even going back to an industry shift from waterfall to agile, that, when you view it through this lens, is an exercise in increasing the reversibility of your decisions as a software engineer. CI and CD increases the reversibility of your decisions. Containerization, feature flags, canaries. You can think of all of these things as increasing the reversibility of your decisions, and that helps you navigate complexity. Okay, you've got a lot more confidence as a developer making a change in a container, throwing it up there, and knowing that you can very quickly revert to an earlier version than you would with a traditional monolith where you have some complicated system to push to production. So if you're in a position where you can select for architectures that encourage reversibility, that will help you with a complex system. Then there's this other thing, chaos engineering. So Netflix, around 2008, moved from a data center to the cloud, from vertically scaled stuff to horizontally scaled stuff. And when you've got thousands and thousands of servers in the cloud, one thing you're guaranteed is that some of them will just spontaneously disappear. It's a feature of the cloud. Early days, they had some stability issues because of an important server would disappear, and then the system would have trouble. So they tried a lot of things. One thing that worked was they scheduled this daemon, basically, to, for each microservice, take one node per day, and during business hours, turn it off. If your system was vulnerable to a single point of failure, if one of your servers was important, then you wouldn't be able to get any work done until you solve this problem. And that's a great way to manage engineers. A very well-defined problem right in front of them, and they solve it. And we don't care how they solve it. We could give them a list of put it in 3 AZs and do X, Y, Z. Who cares? They solve it. And once they solve that problem, however they do it, you don't have to worry about it again. And so many, many, many years go by that Netflix does not have an outage due to a single point of failure. Thought, that worked at a small scale. Maybe it'll work at a big scale. That was Chaos Monkey. Let's try Chaos Kong. Netflix runs in 3 regions, Amazon regions, AWS regions. The control plane does. Over a third of the bits on the internet in North America are Netflix traffic, which if you do the math, it turns out that's a lot. So they're like, okay, well, what if we turn a region off? We'll shut a region down and make sure that the system is resilient to that kind of failure. Caveat. So they can't actually turn a region down, something that AWS has other customers as well in the region. So they simulate turning a region off. And then they move all of that customer traffic over to the other 2, thus ensuring that all of the microservices are built in such a way that this will work, so that when a region does go down, or there is a problem in a region, they can use the same mechanism to recover and remediate from it. So I thought, that worked too. So what's going on here? Well, there's a model, this one comes from Rasmussen, that says there are 3 things that are kind of in the back of people's minds as they go about doing their work. Workload, economics, and safety. And you can think of these as boundaries. And if you cross the boundary, you die. No, you don't actually die, but the business gets hurt. So you can kind of intuitively understand this. If you cross the economic boundary and run out of money, you're out of a job. And intuitively, you kind of probably know how much you cost, give or take, and you probably kind of know how much the resources that you use in terms of cloud spend or whatever, how much they cost. Workload. If you work too hard, you're done. And the same goes for your servers, right? If they're overloaded, then they're not going to be able to get their job done. And again, you probably kind of intuitively know where you are on a burnout scale and your team and the capacity for your servers. Gosh, I hope you do. And then the third one is safety. Again, if your system isn't safe, or if it's close to breaking, if you go over that boundary, you're done. But here's the interesting thing. You probably have no intuition of how close you are to that boundary. Unless you're doing a lot of chaos engineering, because that's what chaos engineering does. It gives you a signal for how safe your system is that over time can give you an intuition of how close to that edge you're actually riding. So here's a formal definition: the facilitation of experiments to uncover systemic weaknesses. And there's a lot of ways to do this, but that's what the chaos engineering tools are designed to do. And so you mentioned a manifesto. This is the manifesto of sorts, principles of chaos, that says, here's the definition of what chaos engineering is, here's how to know if you're doing it, and here are a couple principles for how to do it better. And Netflix built CHAP, a chaos automation platform, which is the most sophisticated instance of chaos engineering that we know of. It's essentially running experiments on the IPC layer of microservices continually during business hours, automatically. So how do we survive the undesirable effects of complex systems? As you're going through your day as an engineer or a sysadmin or just working in software, it's more, if you're not dealing with a complex system yet, it's more and more likely that you will be. And you've got all of these things that you have to optimize for. There is never a right answer for how to do your job in software because there's too many variables to optimize for. And to make matters worse, they change minute to minute. Your boss might say, oh, we need to make this cheaper, and then you have an incident and they're like, oh, forget how much it costs, we need to make it more available. And that's going to change how you pick a solution to tackle your job. So I like this analogy of, think of a well-run kitchen. Hopefully you've had the experience of being in a kitchen for Thanksgiving or Christmas or something like that. And a bunch of people are working on, making dinner. And nobody can say, lift the knife up and then down and then move the carrot and lift the knife, right? Nobody can micromanage. So you've got a bunch of people, probably relatives, and they're working on their stuff, and somehow dinner just happens, right? There might be a little bit of coordination, but somehow dinner just happens. And maybe you've had the experience of being in that kitchen and you finish chopping your celery or whatever, and you're done with that task, and you look up, and all of a sudden you find that you're in the way. Everything was running smoothly until you're done with your task, and now you're just getting in everybody's way. Why is that? Well, it's because humans have a very good ability, innate ability to subconsciously model the behavior of other people when we understand, when we're highly aligned with them towards a goal. So the minute that you no longer have a goal, nobody else can figure out what the hell you're doing. So you're in the way. That makes a very unresilient system. So when you want a resilient system, you want everybody to know what the goal is, and then you don't have to specify, now you chop the celery and whatnot. People will have a mental model of how that works. So this is still being developed, but here are my takeaways for how to navigate complexity, a complex system. First of all, don't try to get rid of the complexity. You're just wasting your time. Instead, embrace it and navigate it. Get good at navigating the complexity. Provide opportunities for teams to practice working together. This is not training. This is practice. So getting people actually doing the things, game days for outages or responding to security incidents or other stuff. Any opportunity that you as a team can have to work together where you're aligned on a goal and you all just kind of figure out a way to reach that goal together will make you better at being a resilient team and a high-performance team. Tolerate inefficiencies. This is one of my favorites as an engineer, because as engineers we think like, oh, efficiency is the ideal, right? Aside from simplicity. Efficiency is great. Actually, efficiency is not so great. Efficient systems are very brittle systems. So you need a system to be inefficient in order to be resilient. And communicate the safety margin. Chaos engineering is one way to do that. Maybe there are others. But I think for software engineers in particular, chaos engineering is a very appealing way to do that. And communicating the safety margin will give you a better intuition of how to go about optimizing for things during your day. Tools don't create resilience. People do. There's a book on this. And if there's any time, I'll take questions.
Thank you, Casey. That was awesome. All right. Any questions?
That was a great presentation. You don't hear much about the FIT, fault injection technology. Why does that, I mean, Chaos Monkey, Chaos Engineering all over the place, but it seems to me what they did, or you guys did at Netflix, I'm sorry, on the kind of fault injection technology, that kind of depth chart, blow it up, and then keep the breadcrumbs. To me, that just seems like a really good way to expose, the Swiss hole. I know the Decker Swiss cheese model of incidents.
It's not Decker's model, but yeah.
Well, I mean, fair enough.
So the Swiss cheese model is reasons. And most people who study resilience would say the Swiss cheese model is not a good way to build depth and defenses of defenses.
Decker doesn't propose that. He says that's the blind spot.
That's
the blind spot is the Swiss cheese model.
Oh, okay.
Yeah, I mean that's why I say he's written quite a bit about that. But
yeah, so the I won't bore you with the academic roots of the model, but so FIT is just a tool that instead of terminating an instance, interjects itself in the IPC layer between services talking to each other, and adds latency or puts the latency at infinity, or just doesn't let two services talk to each other. So it's a very, it's a primitive for doing chaos engineering. CHAP is an automation platform. What CHAP does is it says, okay, it will introspect a service and figure out the microservices available, and then it'll systematically go through okay, for this microservice, how is it deployed? I'm going to clone it. And then as requests come into the system, I'm going to tag those requests a very small amount, say 0.05% of requests going to production. And half of those will go to one of the clones, and the other half will go to the other clone. We can call one of the clones the control group, the other experimental group, and the experimental group will do something weird, like it can't talk to its database, or it can't talk to its downstream dependencies, or it gets a lot of latency, or something like that. And the rest of the request goes through the normal production path. And then when the response is emitted back to the tool, it looks for that and says, oh, you were part of the control group. Okay, let me just record your metrics. And you were part of the experimental group. Let me record your metrics. And it compares those two groups. And if they're generally similar, great. If they deviate, aha, we've uncovered a systemic weakness, and we can alert the microservice owner, hey, when this weird thing happens to your microservice, did you know that the whole system starts emitting a bunch more 500s? So I mean there's a lot of tooling that went into that. Fits a very.
It was actually you actually injected the termination at the actual atomic level of the transaction and blew it up, and you left the path. I mean, looking at the blog article right now.
Yeah. I mean I was there.
That's a different. Anyway, it doesn't matter.
Yeah. So FIT.
I'm just trying to understand why nobody talks about it.
Well, nobody talks about it because it's just a very small primitive.
Okay.
That's the reason.
It doesn't fall under the chaos umbrella. No discussion.
It's used in the chaos platform at Netflix. It was actually rewritten shortly after. So Colton Andrus wrote it. He now runs Gremlin, which is a chaos engineering company. But so while he was at Netflix, my team, the Chaos team, took it over and rewrote it, and then used it in Chaos tools. But it's just a primitive, right? Like Chaos Monkey is not complicated. You could basically write Chaos Monkey with a cron job. Fit, likewise, is just like looking at the communication between different microservices. It just intercepts that, and based on headers in the request context says, oh, do I have to do something interesting here? Naresh at Netflix actually came up with the idea, the concept behind it. Any other questions? Sorry, do we still have time for questions? Okay.
Hey, I was wondering how you go about discovering your safety margins for high fidelity systems, like systems that have zero fault tolerance.
Systems that have zero margin for failure.
Right, banking, healthcare, health systems.
So every tech stack is going to be context specific. What I'll say that's interesting about this is when I first started evangelizing chaos engineering to like the rest of the software world, so about 4 years ago I held Chaos Community Day, where I brought people in from Facebook, Google, as many industries as I could, and the financial companies, they were like, ads, search results, video, whatever. We've got money on the line. We can't be doing any of this like mucking around with stuff in production with money on the line. And we were like, well, okay, do you have outages? Well, yeah. So are you just going to keep having outages and then standing back up and then running as fast as you can and hitting the next wall and then, well, yeah, so chaos engineering might give you a hint that there's a wall in front of you and you can run around it. Like, oh, okay, we'll try it out. So now a lot of banks do chaos engineering. ING has departments where it's part of an internal auditing checklist. Departments can leverage more if they have a chaos engineering program. So then the next year, healthcare companies were like, oh, sure, entertainment, ads, and money. We've got lives on the line. We could never muck with stuff in production when lives are on the line, which was great because when I defined chaos engineering, I pulled the definition from the pinnacle of Western notions of Popperian science. So the clinical trial, that's what it's based on. So I was like, well, guess what? You already do chaos engineering, you just call it something different. A clinical trial is an experiment on a complex system. And you do that with lives on the line. That's how our whole medical industry is built. They're like, oh, yeah, I guess that's true. So now a lot of healthcare companies, not just insurance, but hospitals and other provisioners are looking at chaos engineering as a way to give them that signal of safety. But the actual implementation should be up to the engineers who are in the field and who understand the nuance of high frequency trading and what it would look like to affect that. Chaos engineering is not about creating chaos. In a complex system, the chaos is already there. Chaos engineering is surfacing the chaos so that you understand it a little bit better. So in no case, high frequency trading included, are you going to run an experiment, or in no case should you run an experiment, that you suspect will damage the product. If you think it's going to affect real customers, then don't do it. Fix whatever it is that that's going to go wrong. It's only there to catch stuff that you didn't know about or didn't suspect.
And let's give it another round of applause for the speakers this morning.